Hello, my name is Jiyeon from KAIST. Today I'm going to present my recent work at AdCube, WebVR ad fraud and practical confinement of third-party ads. This is a joint work with KAIST and Columbia University. Virtual reality is the next computing revolution. It's going to change how we play, work, learn, and live. However, to make VR applications, developers might have to devote a significant amount of time to make it work on multiple headsets. And if users want to play with it, they must have the right headsets. WebVR addressed this issue. It's a technology that enables VR on the web. With this, developers can create cross-platform, cross-device VR experiences, allowing them to reach broad audiences, especially internet users. WebVR is supported by major browsers. Also, there are great frameworks helping to build a 3D world. For example, a framework called A-Frame helps easy to develop VR scenes with such intuitive HTML tags as shown in the code. User can open this WebVR site through a browser and start WebVR on the connected headset by pressing the button on the page. There are already amazing use cases in areas, including news, films, and custom business solutions. What we are going to look at in the WebVR environment is the advertising industry. We focus on a situation where advertising is integrated into the virtual scenes. The reason is that online advertising is the most common way for web hosts to make a profit. For this reason, advertising firms are quickly blending with new technologies. As evidence of this, ad service providers have begun to serve advertisers with the means to expose their products or service in 3D space. According to the report from State Farm, a 500% increase in the click-through rate due to the VR ad campaigns, demonstrating the potential of VR ads to attract audience attention. Unfortunately, there is no method for securely displaying ads in WebVR. In 2D space, there is a safe way to render contents from multiple resources using iframe, which isolates the execution of an ad library. However, in the WebVR environment, there are no iframe-like primitives. Instead, it shares a portion of the displayed VR scene. As a consequence, malicious ad library providers can attempt new ad fraud techniques specific to the 3D environment to maximize their profit. In this study, we would like to introduce 4 ad fraud techniques that inflating impressions or click-through rates of advertising in WebVR. First, a blind spot tracking attack exploits the nature of 360-degree vision of VR and places ad entities outside the user's current view. Thus, the adversary is able to increase the number of rendered ad impressions. Similarly, an auxiliary display attack can abuse the user's limited awareness of the browser window that is rendered on the screen. This attack places ad impressions on the user's main monitor during his putting on the headset to maximize ad view counts. In WebVR, a gaze cursor and controllers are used for user interaction. Gaze and controller cursor jacking attacks falsify this means of interaction in the 3D scene and deceive users as if they had clicked on the ad entity without actually clicking on it. The left figure illustrates that an adversary registers a fake gaze cursor at the virtual scene. He also deftly places an ad entity, making victims believe that they are staring at the object belonging to the publisher while simultaneously clicking on the ad. The controller cursor jacking attack works in a similar manner. Thus, both attacks are able to hijack authentic clicks that should be attributed to the first content. To measure the efficacy of proposed attacks, we recruited 82 participants and investigated their response to 4 attack scenarios. And it shows the result. First, the blind spot tracking and abusing auxiliary display attacks were successful with 94% and 100% respectively. The result of two-click checking attacks showed that more than 88% of the participants clicked on the ad entity. Therefore, the result shows the 4 ad fraud techniques are effective in conducting click and impression fraud in WebVR. To defend this, we defined 2 requirements. First, the third-party JavaScript code should place ad entities only within the confined area that the first party specifies. Second, third-party JavaScript code should not be able to alter DOM elements and sensitive entities such as a camera if the first party does not permit doing so. In this study, we propose a defense model called AdCube. AdCube is a JavaScript library that guarantees the aforementioned requirements by limiting the execution of third-party scripts. To enable AdCube, publishers need to include an AdCube code with a security policy. Also, ad service providers should implement advertising behaviors using AdCube APIs. Let's take a look in detail. The following example illustrates an HTML code of a WebVR host. The publisher defines an ad entity using the AdCube tag. This tag has 4 attributes which specify the location and size of the ad. AdCube also provides a security policy that allows an ad script to read and write to entities belonging to the first party. The example code indicates that the ad script can read information such as the location of the box and modify the cylinder with write permission. To sandbox the third-party ad library, AdCube leverages Kaha, a sandbox framework from Google. Kaha sandboxes the execution of guest code from its host page by allowing them to only execute predefined APIs. Thus, AdCube offers a set of APIs that allows the ad script to implement advertising behaviors. The code below creates an ad entity via createElement function, and it sets the attributes that specifies the source of a 3D model and attaches a click event handler to trigger actions such as animation play. The invocation of add element appends this entity to the area that publisher defines by the AdCube tag. Given the ad library and security policy, AdCube resizes the ad entity to fit within the space allowed by the publisher. AdCube does this by calculating the bounding box of the 3D model and scaling it to the allocated space. For the 3D model that play animations, AdCube pre-calculates the maximum size of the bounding box. To this end, we project the 3D ad model into 2D space and sample frames during the animation loop. Because only information for 2 axes is obtained in the 2D projection, we rotate the camera angle and repeat this operation. For the rest of time, I will explain the evaluation of AdCube. We first investigate whether AdCube successfully defends presented ad fraud attacks. By default, AdCube does not set any read and write access to the host entities. This ensures that the third-party code cannot read the sensitive entities and DOM elements, and it also cannot tamper with the authentic cursors. AdCube also prevents in the case that the host grants access permission to the camera entity. In this case, AdCube restricts ads from being placed outside the user's view. Additionally, even when a fake cursor is registered on the camera to trick users, the user can easily recognize it with the label added by AdCube. Therefore, AdCube effectively defends all attack scenarios. For performance measurement, we compared AdCube with two different methods. First, the baseline approach is to run third-party scripts without adding any security layers. Second, the mirroring approach leverages the same origin policy enforcement of the browser by generating a guest page with a different origin from the host page. We evaluated the performance of three approaches in terms of page loading time and frames per second. Compared to the baseline, AdCube produced a negligible FPS drop when rendering a complex demo site of a virtual art museum, and an additional page loading time of 2.3 seconds on average when rendering 9 WebVR sites, thus demonstrating the promising efficacy of AdCube in the wild. Let me finish with the conclusion. In this paper, we have devised 4 new attack variants to conduct WebVR ad fraud. We propose AdCube that allows publishers to confine third-party ad entities. Our experiment results showed that AdCube is able to block ad fraud threats with negligible overheads. Thank you for your attention, and I will be happy to take your question.